Okay, so what we're going to do today is I'm just going to very quickly, like we usually do, I'm just going to go through this Learning Unit 4. We have finished with sort of the official theory for the year. So this Learning Unit 4 is on problem solving using computational thinking. So this particular section you can think of as being kind of a crossover between theory and prac. It's literally, it's the theory of programming, really. So, and this sort of stuff does come up in a couple of the exams and tests that are going forward. And I will show you which sections come up quite frequently in exams between now right through to the end of matric. So the idea here is they're trying to introduce computational thinking as a means of problem solving, or problem solving using computational thinking. And they kind of break it down into bits and pieces. So what they're saying here is the first thing that you should be doing is decomposing a problem. So this is the whole idea, is sort of take a big problem and break it up into small problems. And then you take each one of those small problems and you break that into even smaller problems. And in theory, you could get it right down to the end, which would be where literally every problem can literally be solved with one line of code. You can push it right down to that sort of level. So they'll go through this. I'm not going to read from the book here. We'll just take it. We'll just sort of take it in order as they're going. So they break decomposition down. First of all, they say understanding a problem. That's very important, because often somebody who asks you to write them some software, they're not a computer person. So they don't understand the techniques involved, and often they don't really know how to specify the problem properly, and they'll leave out a whole bunch of stuff. So you as the programmer, you've kind of got to make sure that you chat with them, and so they can understand what exactly the problem is, the sort of things that they might have left out. So you need to fully understand the problem. So that's the first thing, understanding the problem. Then once you fully understand the problem, then you start breaking it down. And you can see on page 58 there, they're just breaking it down to small tasks. And then, like I said, you can take even each of those small tasks and break it down even further, and then combine it into a solution. Okay, so once you've decomposed the problem, then they propose a thing they called IPO, which is the input processing output model. You can just have a peep at that. So it's just sort of what parts of the computer are solving and what parts of the problem. Okay, after decomposition, you get to pattern recognition. We saw these before, and you'll see them again in exercise 2 on the other side of the page here. They're saying to you, you can probably have a look to see if there's any patterns in the solution, because that makes it easier to code. Obviously, because if there's repeating bits and pieces, you just write one piece of code and then you just loop that a whole lot of times. Okay, so there might be existing programs that you can use. For instance, if you need to sort something, I can assure you there are libraries of sorting algorithms, especially in Java. And remember, in Java, we can just import a library and use the code freely. That's the beauty about object-oriented code. Okay, so pattern recognition. So are there existing programs that you could use? Are there pre-written methods that you could use? Is there repeating patterns sort of in the solution? Just anything that you can use to make it a bit easier for yourself. And you'll see that over the page on 60, and we did this before when we were messing with Gr10. You can see there in that in number 3 there, they've got those 3 sort of crosses. There's definitely symmetry in there. I mean, the fact that you've got 3 crosses, that's symmetrical. So if you can draw 1 cross, you just write a routine to make 1 cross, and then just obviously, depending on where you start, is where it's going to draw that cross. And each cross itself is made up of 4 pieces. You can see each leg. So if you just make a piece of code to make 1 leg, you can do that whole program. Okay, you just call it 4 times and then 3 times to do all 3 crosses. So 12 loops, loops within loops, and that whole thing is done. So that's the whole thing behind pattern recognition. If you've got any questions, just shout, eh? I'm going through it quite quickly, so just shout if you've got any questions. Okay, abstraction. So abstraction is kind of the opposite of breaking a big problem into smaller problems. It's kind of the other way. So breaking a big problem into smaller problems, that's what they call a top-down approach. Okay, you've started with the big problem and you work it down to the small problems. So you're working from the top and you're working downwards. Abstraction is more of the opposite way. It's more of a bottom-up approach. So the idea is you've got the small problems, and then what you do is you just zoom into them and you just completely lose focus on everything other than just the small problem that you are on, and you treat that as just a tiny problem completely of its own. Okay, so that's abstraction. It's just forget about almost like they use that example of a camera zooming in. You can no longer see what's around you. Same sort of idea. And the idea being is that once you have solved all the little problems, then by definition, the big problem is solved. Okay, so that's an abstraction kind of model there. And then after abstraction, you get to algorithms. And algorithms in computer science, there are tons of algorithms for all sorts of things. These are already pre-written. Like I said, if you're going to do sorting, there's all types of sorting, and some of them are more efficient than others. There's bubble sorts and shell sorts and selection sorts, all with different algorithms. And we will learn some of these as we're going along. Okay, so the idea is see if you can recognize any algorithms in your own experience. And as you're getting more experience here, you'll start knowing how to solve some of these algorithms. Okay, they talk about data structure. How's your data going to be represented in your program? What variables do you need, etc., etc. Then they move on to flowcharts. Flowcharts come up. Okay, so in tests and exams, you will see flowcharts. Flowcharts is more of a pictorial representation of your program. So if you are planning your program on paper, you can use a flowchart with pictures to kind of lay out the structure of your program, the algorithm of your program, right? And you can see there are five basic symbols that you need for your algorithm. You've got that sort of oblong at the top. That's the start and the end. And then you've got a rectangle. That's where you're going to put in your program statements in. Then you kind of got that skewed parallelogram looking thing there, which is for input and output. So if you're asking for something from the keyboard or you're outputting something to the display, you use that one. The diamond shape is a decision because it's got two sides to it. So it will ask a question, is A bigger than 5? If it's yes, an arrow goes out from the right. If it's no, an arrow goes out from the left, because there's a branch in your program. There's an if statement. So the diamond is for an if statement. And then we've got connecting arrows. Okay, so if you want to do these in Word, as a matter of fact, you can go to, if you open up Word and you go to Insert and you go to Shape, you'll get a whole bunch come up, and there's a whole section of flowcharting shapes built into Word. Okay, so when you're doing some of these exercises, feel free to use that. So they give you a couple of examples there of flowcharts. You can see what each one, you've got the start and the end and the oblong. You've got inputs and displays in the parallelogram-y looking thing. And then you've got statements in the square. Okay, I noticed that none of these ones here have an if statement, probably because they couldn't draw long arrows or something. I don't know. But you'll see them later on. Okay, so after flowcharts, another way that you can represent your program and its structure and its algorithm is using pseudocode. Here's another bit. This one is going to come up, I guarantee you, all the way to grade 12. Even in your grade 12 final paper, there will be a question on pseudocode. So you'll need to get this. You'll need to get this down pat. So pseudocode is a bit more. It's a non-computer language specific way of writing your program. Okay, and you can use pseudocode, and then you can give that pseudocode to any programmer, and they would then convert it into Java or C or whatever program they're going to write for you. So pseudocode there are definitely some rules to it. You'll see it starts, if we look at on page 64 there, sort of in that little table on the left, you can see it has a begin and an end, the word begin and the word end, marking blocks of code, okay? And in fact, back in the day, there were programming languages that were like this, right? Pascal was one of these. When you program in Pascal, it had these begin and ends in it. It's not like that anymore. Okay, so there you can see the rules for pseudocode are there. You start with begin and you finish with end, and there's indentation. Okay, so you then indent. From there, the margin moves in. So you must look like that. You've got each line of your pseudocode. It's very much more English than it is sort of a programming language. You don't use the equal sign. You've got like a left arrow. Okay, they call it assignment. It's even called assignment in Java. If you're looking for equals, you remember in Java, it's equals equals, two equal signs. A single equal sign is assignment. You're taking a value and assigning it to a variable. There's no semicolons at the end of the statement. Okay, like I said, this is not Java-y. Okay, this is just English. You don't have to specify your variable types, so you can just use the names. And you don't use method names. So you don't use like bug move. You just say move bug one left or something like that. You can use the mathematical symbols, and you use the word input if you want to enter something from the keyboard, and you use the word display if you're going to display something to the screen. So they give you some examples there of what this thing looks like, and then they give you the Java equivalent sort of on the right-hand side. So the left-hand side, and in an exam, if they ask you to write pseudocode and you write Java statements, they will give you 0. Okay, they're brutal with this thing. Pseudocode is pseudocode, Java is Java. So you need to get used to writing pseudocode. Very important. And like I said, it comes up in test after test, exam after exam. I'm now on page 666. Okay, we're at 4.6 on coding. So coding now, we're now beyond the algorithm stage. We have completed our the planning. We've got our algorithm, whether it's a flow chart or whether it's a pseudocode or whether it's a hybrid of both. And we now want to start coding. So they are now telling you what makes a good program. Okay, the first one is user friendliness. It must be easy to use, okay, for the user. So if you ask them a question and they must input some information, you must be very clear as to what they must enter. Okay, so that's user friendliness. Then keep the user interface simple. That's the next thing. Okay, so don't make it very complicated at all. Okay, make it very readable. Okay, they give you some examples here of good and bad user interfaces. Readability. 4.6.3 at the bottom of page 67. The readability they are referring to there is not for the user this time. It's if you have to give your program to another programmer. Let's say you leave the company and you got to give your program to another programmer. How readable is your program? Have you stuck with the proper naming conventions and all that sort of thing, right? So it must be very readable and it must be well commented, that sort of thing. So that's just good programming. And on page 68, they will tell you there what makes a very readable program, right? Descriptive variable names. I've told you that right from grade 4. Okay, use meaningful names for your variables. One statement on a line. Remember with Java, as long as you got a semicolon, you don't have to come to the next line. You could write the next statement right next to it. Your whole program could be one massive long line, one line. So as long as the semicolons are in the right place, the program will still work, but it's terrible to read. Proper indentation, comments, separate your code nicely into code blocks, and follow the naming conventions, right? So that makes it very readable. 4.6.4, this is quite important. This comes up quite often in an exam question. They will ask you to explain what the 3 types of programming errors might be. So the first type is a syntax error. That's literally a typing error. So if you type a command and you spell it wrong, and the compiler will underline it for you and say, I don't know what this is, or you've left out a semicolon or something like that. So it's more like typos, right? Those are syntax errors. Easily fixable because your compiler normally marks it for you and says, hey, there's a problem here, fix this. The next type of error is a runtime error, also makes itself very apparent. Okay, this is not a compiler error. Your program will compile properly. This is more an error that you have made by not catching certain situations. For example, you might ask the person to input a number so that you could, say, find the square root of it. And you're not watching out if they put a negative number in. So if they put a negative number in, then obviously the square root of a negative number is undefined, and you're going to get a runtime error. So that's an error in your code that the compiler won't pick up because there was nothing syntactically wrong with your program, but it was an error condition that you never trapped. So that's what you've got to be careful of. But they do come up normally during testing. You'll find them. The last type of error is by far the worst. Okay, it's a logical error. Okay, it's some condition in your program that you never took into account. And there are some very famous examples of this in code that in sort of rockets they sent into space, and the whole thing either blew up or never went where it wanted to go because there were logical errors in the program, and they weren't caught during the testing phase, and something awful happened. Some if statement ran, and there was nothing to cater for one of the cases or something like that. So those are logical errors, and they are by far the most difficult to find. And they can often be devastating to your program. Okay, we then do a section here on testing and how to test. So normally you would test, I'm on page 69 here. Normally you would test with just normal standard data. So you would put normal, every run of the day mill that you would expect people to put in. Then you need to test what they call extreme data, like right at the edges. So if you ask them to put in their age and you are allowing them to put in an integer, they test it as if they put the age in at 2.1 billion, because that's the biggest integer you could have, for example. So make sure that things don't go weird if people put in weird stuff. Then put in abnormal stuff. Like if you're asking for an age, what happens if you put -5 in there? Okay, so abnormal data, something that it couldn't be, but you must cater for those situations. Okay, I like to call it idiot proofing. So if you're writing software, I'm telling you now, more than 60% of your total software development time, more than that, probably 3/4, 75%, is idiot proofing, trying to work out what some idiot is going to type in to the keyboard and make sure that they can't break your program. Okay, so you can read through the section on testing there. Okay, the next one here on 4.7.3, this is super important. Like I said, flowcharts come up, pseudocode comes up, and this one here, trace tables, comes up all the time in tests and exams. Okay, how to make a trace table. So a trace table is basically a sort of a paper representation of how your program is running. And there on the bottom of page 71, they've actually put a trace table there. Okay, so down the left-hand side, you've got your line numbers of your program, and then you've got a column for each variable. And then basically what you're doing is you're saying right at line 1, and num1 becomes a 9. Okay, I'm looking at that image on page 71. Okay, then on line 3, num2 becomes a 4. Okay, and then on line 4, num3 becomes a 2. And you can see further down on line 9, num1 becomes a 12. So it's tracing, that's why they call it a trace table. It's tracing the values of your variables on the different line numbers of your program as your program runs. Okay, once we get back to school, I will show you how we can do this sort of thing in NetBeans. Okay, so NetBeans has this fantastic debugger built into it, and we can actually get it to stop at certain places in the program. Okay, we can halt the program execution, and we can investigate what are the values of variables at that point in time. So you use it for debugging. And a trace table is for the same thing. It's for testing and debugging. Okay, if your program does not work as you expect it, then often a trace table, you'll be able to see where it went wrong. Some variable changed to a value that you weren't expecting it to change to. And you hadn't noticed it until you wrote it out on paper in a trace table. So you must know how to make a trace table. That is super important. You're going to get this question plenty, and it really is money for jam. Okay, these trace tables they're dead simple. As is pseudocode, real easy. It's easy marks in an exam or a test. Okay, and the very last stage, okay, I'm on page 73 now, is just evaluation and optimizing. That's section 4.8. Okay, 4.8. And that's just kind of, once you've coded your program, to have an objective look at it to see, could I have optimized it some way? Could I have made some of my loops a bit faster? Am I doing something inside of the loop that I can safely do outside of the loop? So I only do it once instead of doing it every loop, you know? So could I optimize stuff for speed and memory? Okay, so that's as far as I'm going to go. I'm not going to do anything else here in this live session. The rest of this, from here to the end, is examples. Okay, so I want you to kind of work through those examples. Let me just stop the recording here.